Alright, so we're going to be discussing Leetcode problem number 3249, which is count the number of good nodes. So first I'll go over the problem statement, then I'll talk about the example, and then we'll be moving on to the solution part. So there is an undirected tree with n nodes labeled from 0 to n minus 1 and rooted at node 0. You're given a 2D integer array, edges of length n minus 1, where edges of I is equal to ai comma bi, and it indicates that there is an edge between nodes ai and bi in the tree. So it's basically an undirected graph itself, right? A node is good if all the subtrees rooted at its children have the same size. So a node would be considered good if all subtrees that are rooted at its children have the same size. So we need the same subtree size for that particular node, right? For each of the children, right? So return the number of good nodes in the given tree. A subtree of a tree name is tree consisting of node in tree name and all of its descendants. Okay, so this is basically redundant information. We don't need this. The most important information given to us is this: a node is good if all the subtrees rooted at its children have the same size. Okay, so let us go over basically this tree. So we have been given edges vector or vector type, right? So basically first edge is 0 to 1, second edge is 0 to 2, third edge is given to us as 1 to 3, then 1 to 4, then this is 2 to 5 and 2 to 6. So basically this is the tree that is being formed, and we need to return the nodes that are good. So good node is basically which has same subtree size in all its children. So children of 0 are basically 1 and 2, right? So we need to see the subtree size of 1 and the subtree size of 2. Both have a subtree size of 3, so that means 0 is a good node. For 1, 2, if you check, 3 and 4, the subtrees of 1, basically left child and right child, are 1 and 1 respectively, the subtree sizes. Therefore 1 is also a good node, and 2 similarly is a good node, and 3, 4, 5, 6, all these are leaf nodes, so they are also indirectly good nodes because they have no subtree falling under those. So the subtree size is 0 for each of these leaf nodes. So basically we have total of 7 nodes which are good in this tree. So that's the answer, 7. For this example, you can see we have this tree, and you can see that all the leaf nodes that are coming, the leaf nodes would obviously always be counted as good node because they don't have any subtree. So basically we can increase the count. So 1, 2, 3, 4, 5 for the leaf nodes, 5 leaves, plus let us see 3 is basically having equal subtree sizes in the left child and the right child. So basically one node, 5 leaves plus 1 internal node, so that basically gives us the answer 6. Now why is not 0 or 1 or 2 considered as a good node? Because if you see, for the left child we have 3 nodes in the subtree of its left child, while for its right child we only have 1 node. So there's a disbalance here, so that is why it would not be counted as a good node. Similarly for 1, we have 1, 2, 3, 4, 5 nodes in the left subtree and only 1 node in the right subtree. So you can see there is an imbalance here again, so it is not considered a good node. Similarly for 0, we have 7 nodes here and 1 node only here, so again the imbalance, so we do not count it as a good node. That is why 6 is the answer. Now another example is this one. So now you can see that it is not a binary tree given to us, it is a normal tree, so we'll have to consider it as a graph problem, right? So for 0, if you see, for 0 the children of 0 are basically 9, 5 and 1, right? So for 9, what is the subtree size here? The subtree size is 4. Under 5, the subtree size is basically 4 again, and for 1 as well, we have the subtree size is 4. So therefore 0 is a good node, 0 would be considered a good node. That is why it's marked as blue or highlighted as blue. But for 9, if you check, 9 has 1 in its left child and 2 as the subtree size of its right child. So therefore 9 won't be considered as a good node, therefore it is not marked with blue. For 12, 10 and 11, you can see for 12, 11, 8, 4, 4, 3, 2, all these are leaves, so these would definitely be considered as the good nodes. For 10, only 1 is falling under it, so therefore this is also a good node. Similarly for 5, 6 and 7, all of these nodes are falling under it and there are no additional subtrees for that, so basically these are also considered as good nodes. And for 1, we can see that it's all its children have subtree sizes equal to 1, so therefore 1 is also considered a good node. So therefore the count is basically 9. Sorry, the count is basically 12 except the node 9, right? So that is the answer. So now let us go over the solution. So I have posted my solution, and let us see how do we approach this. So we're going to approach it using a normal DFS, because you can see we are recursively traversing the tree. So intuition is that we are given a tree which is an undirected graph with no cycles, and we want to find out how many nodes are good. And a node is considered good if all its immediate child subtrees, not the full tree, have the same size. All its immediate child subtrees have the same size, and the leaves are good, right? That is, leaves are basically nodes with no children. Now the idea is to perform a post-order DFS from the root node, that is by computing the size of each subtree. For each node, check all if all its child subtrees have the same size, and count the node as good if the condition holds. So now approach is as follows. So we firstly build the tree, use an adjacency list to represent the undirected graph. Then we apply the post-order DFS, right? So post-order DFS recursively compute the subtree sizes at each node, track the size of the child subtrees, and check if all are equal. And if they are, increment the global good nodes counter. Complexity, as for that, time complexity, since we are performing DFS, it visits each node once, so it would be O of n, and space complexity would be for adjacency list and recursion stack O of n again. So now coming over to the code part, this is our main function count good nodes, which takes a vector of type int edges, right? So this is basically containing all the edges between the nodes, and we assign n as the integer edges dot size plus 1, that is the number of nodes. Now we have also defined our adjacency list, which is of vector of int type, which will denote the undirected graph, and answer is basically the count of good nodes, that is the nodes that have same subtree size for each of its child. So we have stored that in answer, and answer is 0 initially, right? So first we resize the adjacency list with the n, and we basically make our adjacency list or the undirected graph. So for each edge we visit, we basically make the undirected graph. From node u to v, we have undirected node, so we make this undirected edge, so we make this graph, and then we pass then we call the function DFS from node 0. So this is the node, and -1 is basically denoting the parent. So DFS from node 0, which is root with 0, root with no parent, and finally we return answer, which would be returned from the above function, that is DFS. So DFS is basically the recursive function to compute the subtree sizes for this particular node. So we have node and its corresponding parent, right? So the parent from which it occurs. So we assign total nodes as 0 initially, and we have kept a flag that is going to tell us whether the node is good or not. So that is boolean. Bool is good function. Bool is good variable. We have set it initially to true, right? And also subtree size we've stored as -1, that is the size of the first child's subtree. So this is an arbitrary value, -1. You can choose any other value, right? Which is negative, right? Subtree size is -1. Now going over, basically we are performing DFS, right? So for going over each neighboring node, we go over this using the syntax for auto neighbor in adjacency of node, right? So in the let us say this is the node, and these are basically the neighbors, right? So these are the neighbors of this node. So we get that from the adjacency list. If the neighbor is equal to parent, that is, if this neighbor is equal to the parent, that means we have to avoid going back to the parent. So if in case this was some the structure of the graph, if the parent, that is initially 0, right? So if neighbor actually becomes the parent itself, then we have to continue. We don't want to go to the parent, because we are considering the subtree sizes of the children, right? So we have to consider only the subtree size of the children itself, right? So we set the current size as DFS of neighbor and node. So DFS, we pass neighbor as the current node, and the node that we had considered in the function would be our basically parent, would become our parent of this particular neighbor. So this is the neighbor, and node becomes the parent. So if subtree size equal to 1, that is, if the size equal to 1, then we store this size of the first child subtree in subtree size. So subtree size becomes equal to current size, as you can see here, and subtree size is basically containing the size of the first child's subtree. As if the current size that is that we get from the DFS function is not equal to subtree size, then we set is good is false. That is, we have found a subtree which has a size differing from the other children, right? So we set is good is equal to false, and the total nodes, when we've checked all these conditions, total nodes we add as the current size. In the total nodes we add the current size, and now we check if our basically current node is good. If in case our current node is good, then we update the answer by incrementing it by 1. That is, we have found a good node, right? The current node that we are at, we have found a good node, and we increment the answer. So answer we have added by value by 1. And finally we return the total nodes plus 1, that is, current node is added along with the sizes of the subtree that we have received, right, for that particular current node. So this is how you perform DFS, and that's the solution for the problem.